What is up, YouTube? Man, I've been wanting to use that intro for like the longest time, for like maybe like 2 months now, but I just keep forgetting. I just keep forgetting to not use that intro, but I finally used it today. Maybe I'll use it in 10 videos later. But it's Thanksgiving Day. It's Thursday right now, November 27th. Very happy of 2025. So I'm in a good mood. I remember to use the introduction. But anyways, in this video, we'll be talking about set identities. Alright? And I'm going to be covering some very important things about these set identities and maybe some mistakes that people make along the way when performing these identities, right? Because when you're using formulas or equations or identities, sometimes you make mistakes. Sometimes you don't interpret the identity right. So the first one we're talking about is the idempotent law. Idempotent law basically states that if you take the union of a set with itself, you just get the same set. And if you take the intersection of a set with itself, again, you just get the same set. And this logically makes sense, right? If you had the set 1, 2, and you took the intersection of 1, 2 with 1, 2, well, it's just the same exact numbers, right? They're the same exact numbers. The intersection between these is equal to the same thing. Right? That's kind of the same logic you have here. That's actually kind of the same logic you have here, right? If you take the union of the two of the same sets, it just removes all the repeats. You get the same thing. Now, as you may know, the order in which you calculate unions and intersections, especially with parentheses, matter, right? And even with complements, right? There's an order of operations for set operations. But the Associative Law states that if you have unions and unions and unions together, then you could just change the order however you want, right? And the statements are still equivalent, just like this. You can calculate A union B first, and then take the union with C, and this will be equivalent to B union C first with the union of A, right? These are both equivalent no matter the order in which you calculate the unions, all right? Now, an important thing to note about the Associative Law is that you need the same set operation in order for this to happen, right? Notice how both of these guys are unions here, right? And notice how both of these guys are intersections here. So in order to perform the Associative Law, you need the same set operations, right? And let's say we had a case like this, right? A union B intersection C. You would not be able to switch the placement of the parentheses to get B intersection C first. That's just not how it works, right? You're just going to get a different answer if that's the case. So keep in mind, the Associative Law requires you to have 2, 3, 4 unions, doesn't matter. They all just need to be the same operation in order for you to be able to switch the order of computation. So the next law is the Commutative Law, Commutative Law, however you like to pronounce it. And we have A union B is equal to B union A. This is how it works, right? We have A union B with B union A, and we also have A intersection B is equal to B intersection A. Now, the important thing about the commutative law is that this works, right? Just like the associative law, this works with multiple unions or multiple intersections. So we have A union B, union C, union D. We can calculate this in whatever order we want. We can write down B union C, union D, union A with no particular order of choice, right? I just chose random letters from here. And this would be equivalent to this, right? It doesn't matter what order we calculate it. And we can also change all of these to intersections, and the result would still be the same. Okay? So for the commutative law, you just, as long as you have the same set operations, again, you could just change the order willy-nilly however you want. This next law is called the distributive law. And the key thing to note about the distributive law is that you need opposite set operations. So we have a union here, and we have an intersection right over here. So these two are opposites, right? And that's when you can use the distributive law, especially if they're in parentheses as well. Now, if these were both unions, there would be simply no point in using distributive law. You can just use associative, or you could use commutative, however order you want to calculate it, whichever law you want to use. So keep in mind, distributive law needs a union in an intersection or an intersection in the union inside parentheses, like so. And what we can do is actually we can distribute, right? We can sort of distribute this union of A onto union B and union C. And as you can tell, if you have union A with B, you have union A with B here. And a union A with C, we have a union A with C here. And notice how the intersection's in the center right here? So basically all we did was put this union A in front of B like so, and a union A in front of C, like so. And that's the same for the intersection case, right? We have a intersection A, and all we did was slap it in front of the B and the C. So we get union A, intersection A with intersection B, and intersection A with intersection C. And we have the union in the center between these parentheses. All right, so the distributive law, basically, all in all, you need either union and intersection or an intersection and a union. Now, an important thing to note is that throughout this entire video, when we're talking about laws, we're talking about sets. And here's the thing about sets. These sets can be a combination of sets as well. So for example, A could have been an equation like so. You could have been like D union F, right? Symmetric difference of E, right? So this A could have been an entire operation right here. Right, and we can still use the distributive law like so, as long as we plug in A properly here. That's the same for B. B could have been this entire equation as well. B could have been something else, right? B could have been this. As long as we plug in B in the right spot for the distributive law, all of these still work. All right. So keep in mind, A doesn't have to be a singular set. It can be an entire order or a list of operations, and same for B and C. Same for every set that I'm showing related to laws inside of this video. This is the identity law. So if you take the union of any set with the null set, you just get the same set, right? So if you combine nothing with something, you just get the same something at the end, okay? And a little refresher, the null set is just an empty set. It's just a set with nothing inside of it, right? It's just brackets. Now how about this? If you take the intersection of the universal set with A, you just get A. So the universal set is basically just a set that's typically defined at the beginning of the problem and is by convention a U. All right, so by convention it's a U. Typically it's defined at the beginning of a problem. Okay, and it basically is a set of every single possible value within the context of your problem, or even with the context of literally everything. Okay, if it's not defined, it's probably just talking about everything. But the universal set is just think of it as everything. If you take the intersection of A with everything, you just get A, right? This right here is the domination law, and for those of you that like domination, you'll like this law a lot. All right, okay, what am I even talking about, bro? I really hope that job recruiters don't eventually see my videos, because I'm gonna put this shit on my resume. If they see this video, bro, and they heard me say that, oh, I'm cooked, bro. I'm losing the interview. They're gonna pull up this clip. And they're gonna be like, yo, we're not hiring this guy. But this is domination law. We have A intersection with the null set, right? If you take the intersection of nothing with something, shit, you're just gonna get nothing, bro. Like, it's just gonna be nothing, okay? And this is logical. You don't even need to remember the law identity. You'll just know that if you take the intersection of nothing with something, there's no intersection, right? It's just nothing, so you get nothing in the end. And if you take the union of the universal set, oops, this will be a U. If you take the union with the universal set with any single set, right? Remember, any set could mean a combination of sets. This could have been D exclusive or E, or symmetric difference E minus F, right? Difference F. This A could be literally any set. If you take the union with the universal set, you just get the universal set, right? You just get everything. So this is the double complement law, and this logically makes sense, right? If you say not for any sentence, right, complements essentially a not, then you get the same thing. So you are not stupid. That means you are not stupid, but you are not stupid, right? If you're canceling out the previous not, guess what happens? I'm just basically calling you stupid. So if someone walks up to you and say you're not stupid, don't take that as a compliment, man. They're just calling you stupid. Just like how I am not into femboys. Figured that one out. Just saying that's 4 knots. Figured that one out. But this double complement law, you take 2 complements, this complement cancels the other complement to just get A. So this is the complement law. Basically, if you take the intersection of A with the complement of itself, you just get the null set, right? And by definition, the complement of A is just everything that A isn't. So if you take the intersection between A and everything that A isn't, there would be no intersection, right? So logically, you would get the null set. Same for this. If you take the union of A with everything that A isn't, then you just get the universal set, because everything that A isn't is the rest of the universal set, right? If you combine A with the rest of the universal set, you just get the universal set. And the universal set, the complement of the universal set is just nothing, right? Universal set is everything. So what's the opposite of everything? It's just nothing. And we have this exact opposite dilemma, right? We have the complement of the null set. That's just the universal set, right? The complement of everything, right? The opposite of nothing, the opposite of nothing is everything, right? That just makes sense. This is basically, I'm just interpreting these in words for you guys. For those of you that are computer electrical engineers, are going to really like this law a lot. And this is De Morgan's law or De Morgan's theorem. For those of you that aren't computer electrical engineers, they use this to simplify circuits a lot. Okay, so De Morgan's law, very useful. But basically what it is that if you take the union of A and B and then complement the entire thing. So you need a complement over the entire thing. You can't have a complement on just A or just B. You need a complement on the entire thing. Right? You can separate this complement. So you can distribute this complement onto A and B individually, but you need to flip this union upside down. Okay? It can go the other way around, right? You can turn this into this as well, right? All of these laws you can go backwards as well. Same for this, right? You have the complement of A intersection B, and you can just distribute this complement over A and over B. And remember, all you need to do at the end of De Morgan's theorem or De Morgan's law is just flip the intersection into union and vice versa, right? Flip the union into an intersection or flip the intersection into a union. Last one is called the absorption law, and this one's fairly simple, right? If you have A with the intersection of B, but you take the union of A with this set, then you just get A, okay? And think about it like this. This B can be any set. And any set could also mean, right? This could have been D union E minus F symmetric difference G, right? B can be anything. So as long as E is taken as the intersection of literally any set, and that could have been an entire operation like this, right? Then the final result will be A as long as you take the union at the very end. Also, another thing is this, right? A intersection with A union B, and remember B can be any set, any order of sets, right? Even an entire equation of sets, right? But as long as A is taken with the union of B of just any set, and then you take the intersection of this with this guy, then you just get A at the end. Okay? This is the absorption law. Now, the final thing I would like to talk about is how unions and logical operators are very similar. So this is the OR logical operator. This right here is the OR. And this right here is the AND logical operator. Okay? And matter of fact, intersection is very similar to AND. And union is very similar to OR. So similar that when you are doing set proofs, a lot of the times, you can actually just completely swap out, right? By the definition, you can say, by the definition of union, by the definition of intersection, and then you can write down this. You can just replace all the intersections inside of your set equation with AND operators. You can replace all the unions inside of your set equation with OR operators. And this will work when you're doing set proofs. But I don't know. I don't know if I want to do set proofs. Those are, I really hate making the proof videos, and they don't really get that many views. Actually, I think they actually get quite a bit of views. Actually, those are my most viewed videos in discrete math. I don't know what I'm talking about. But I just hate making them. Oh my god, they're just so tedious to make. They take a really long time. They take like an hour and 30. Like most of these take like 45 minutes, 30 minutes to film. Those take like an hour and 30. I don't want to do that. But if you guys want it, sure. Fuck hell yeah, I'll make them, bro. But anyways, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.